looks like it's probably working. There's no one in Zoom to double check for us, but if the recording is bad, it's unfixable. So it's a good thing to try to make sure it's working before we get started. But welcome back, everyone. We're now over here in section 10.3. We're nearly done with it, but it was kind of a struggle. I didn't remember my digital pen, so class just felt different. I appreciate everyone's patience on getting through that. Once we complete section 10.3, next new bit of information on our way to get through the hypothesis testing procedure is the test statistic Z. We mentioned really all we're doing with that test statistic Z is we're doing Z-scores all over again. So the value in question is going to be the p-hat, the mean is going to be p-naught, and the standard deviation will be the standard error estimated down here. So once that's done in section 10.4, we're ready for the full procedure in sections 10.5. I got a little nervous today that we might finish like 15 minutes early. So I did put it on the document here early, right before class today. But if we open that one up, it's probably just to look at some of the formulas for a little bit. We won't make too much headway in that section tonight. But that's my spiel for the announcements today. Any questions or comments, folks, or problems to start us off today or anything like that? Okay, well, other thing to mention, after we get through our class today and our class on Wednesday, we'll be changing gears and talking about the third exam. We'll spend all Thursday reviewing for that exam. So if you find any problems that you'd like to bring to class that seems like it'd be good problems to review, I'd be happy to take a look at them. And I was going to say something additional. Oh, I remembered what that was. I do have the sample exam 3 posted here and the sample exam version 2, but I'll bring extra problems when we come for our Thursday's review. So it'll be problems that are definitely new to us. But then let's now go to our section 10.3. We're ready to get started. And section 10.3, everything is based off of this, the central limit theorem, just so like it was with the confidence interval procedure. So we started our problem by measuring the center. Now we can add this to the notes finally in a reasonable way. We measure the center in this kind of way. We measure the variability, or you can say the spread, how spread out data is. Let's call it variability. Then we use our rule 3. It's really that entire statement there. And this tells us the shape. But then a good question every time you look at this theorem is the center, the variability, and the shape of what exactly? The thing to always remember, we need to remind ourselves is when we go to calculate the statistic p-hat, we're pulling from a second population, a population that, if the conditions are just right, is normally distributed, centered right at the true but unknown value we're hunting for, and with this as the variability, that equation there. So putting that all together, in our problem, we measured the center of variability, and we said the shape is approximately normal. This is what it finally allows us to do probability computations. So they were asking us questions. Would you be surprised to observe a sample proportion as small as p-hat is 0.13? We calculated that probability, and the only reason we used less than is because of the hypotheses. Let me recopy that. Having a less than right there. Sorry, I scrolled a little too far. So after finding that probability, we compared against the significance level alpha. And if it's right down up here, if this was greater than alpha, like it is in this case, we failed to reject the null hypothesis. If this was less than alpha at 0.05, we would reject the null hypothesis and conclude we have significant evidence that the alternative hypothesis is actually true. And so there's this little table here. A better version of that table will be in the next section notes that organizes the information for us. We're looking for a p-value smaller than alpha to reject the null hypothesis. But here it turned out to be huge and we failed to reject. Then we tried it again. We said, well, what if p-hat was 0.12? The probability that p-hat, the statistic, is less than 0.12 came out at 0.0158. That value was less than alpha, so we said, yes, this is surprising. And this is the situation where we do reject the null in favor of the alternative hypothesis, HA. All these were just scenarios. In part D, our real statistic wasn't 0.12. It wasn't 0.13. We're just wondering what would happen if it was. So that's why it says here in part E, test the null and alternative hypothesis using now the original sample data. So let's plug the hypotheses down here just for easy reference. And here's our next run at this. First thing to take a look at is we have a less than direction in our alternative hypothesis. So we have to maintain that directionality and write probability p hat less than, and now we need to go to the original sample data. This problem is so long and it was split across a day, so I forget what this sample data even looked like. Let's go and cite that information. At the very top, this has been rewritten. We found that the sample size was 1,386, and the number of successes was the 172. Not sure why I called it X. This is actually a screenshot from the notes from last semester. I guess I used X a lot in that case. Then coming down back here, it's kind of hard to know where to park these things so they're not too in the way. Let's just throw it right here for the moment. We're now ready to find our original sample data, and here's where it goes. We had 172 successes out of a sample size 1386. So that goes in, and that's going to be the proportion that the probability that we calculate. I always forget that in these notes. I started with the probability symbol here, but if you save a little bit of space, not a bad idea to call it a p-value. We'll start to call it officially a p-value in the next section notes, but I felt like not a bad idea to call it that now, so we just get into the habit. So the p-value is going to be found in this way, and that means we need some information, some population characteristics on that distribution. Let's take a look at what we had. The mean at p hat was 0.14, so it goes right exactly there. Let me draw this in just so it's available as well. Sigma at p hat, this is the variability, or you could call it the standard error if you prefer, is 0.0093. And our original sample data, 172 over 386, well, that is our p hat, but I'm not sure where to put it on the scale. So let's just calculate it quickly here, just to get a feel for where it even is. So 172 divided by 1386 gives us a 0.1240. I'm not trying to use any approximation here. I'll be throwing that fraction to the calculator exactly. But it's good to know that our statistic is just a little bit to the right of this one. So somewhere right around here. So here's 172 over 1386. It goes into that location, and because of the less than right here, that means we're shading off to the left. We want to accumulate all of this area, and that area, whatever it happens to be, that is the p-value. So probabilities are areas. That means the p-value, which is a probability, is also an area. And now this becomes a review question in section 6.5 of just calculating a probability off a normal distribution. In this problem, we can say that the input number 1, which is lower, will be negative 10 power 99. We're accumulating area going to the left without stopping. Let me make that a more readable 99. This is input number 2, the upper value. And that's input number 3 for the mean, input number 4 for the standard deviation. So all that goes into the calculator. We always use normal CDF for this process since we're looking for area. And we're just about there. Any questions so far, folks, to this stage? Yeah.
The upper value, how come we didn't put the 124 on there? Why did we put the 172 on
You know, I think either value would have worked, but I think my thought of using this instead was, I was just going to put the whole fraction into the normal CDF function just directly. That way I'm not too worried about rounding errors.
Okay.
But in this problem, if you gave it 4 decimal places of accuracy, you're probably in pretty decent shape. I forgot to put rounding information on this. Typically, they're going to say to round to 4 decimal places. Let me just double check if I had it somewhere here. Oh yeah, there it is, round to 4 decimal places. And so maybe another thought, I wasn't actually thinking this, but a good thought to also include, is if we're trying to round our p-value here to 4 decimal places, it might not be a bad idea to just put the fraction in exactly. Or if you do round it to at least 4 places, but 5 places would be even better, just to make sure we have a more accurate answer going in before we round the final thing to 4 places. So back over here, we're ready to throw this all into the calculator. Any other questions so far? Okay, so it'll be second vars to start us out. P-values are always normal CDF problems, so we'll go to option 2. And lower is negative 10 power 99. Let me type it in so it just looks like how we wrote it in. The upper value is 172 divided by 1386. And a decimal approximation is okay there. Now mu is 0.14. Hey, it looks like that copied in from last night. Sigma is 0.0093, so it looks like we're ready to go. Okay, enter on that a couple times, and here's what we get for our p-value. To 4 decimal places, this will round to a 0.0436. Let's throw that in there, 0.0436. We did it, folks. That's our third p-value computation. Any questions at all on attaining that number? Okay, once we get that number, well, it said strictly, test the null and alternative hypothesis. They're not asking us questions of, would you be surprised? We're now actually doing the real test. Recall, this is an informal example of doing a full hypothesis test. So here's what I would do right away. The p-value equals 0.0436. We need to compare it against alpha, whatever it was stated in the problem. That alpha is at 0.05 for the significance level. And we have less than here. The p-value is smaller than the significance level alpha. And so that's telling us for original sample data, our null hypothesis of, and where did that null hypothesis go? There it is. Our null hypothesis of p equals 0.14 is suddenly looking suspicious. If the probability of attaining a statistic as extreme as 172 over 386 or more extreme is 0.0436, then we have very surprising data. It's incompatible with the null hypothesis, specifically because the p-value is less than our cutoff, our benchmark for enough evidence to reject the null. So it's a good idea right at this step to say what we're about to do. Here, we will reject H naught. It's tossed out of the whole problem in favor of HA. The alternative hypothesis is now the better looking statement once we've considered our actual data. So what we have to do next is what we've been doing all class along pretty much. Every single time we saw these words, practical interpretation, it was really about confidence intervals and hypothesis testing. That was our whole objective there, to get used to making those statements so that when we get down to here, we need to say what it means to favor the alternative hypothesis, to have evidence for it. But what we did in part A also helps us answer that question. Before we go to write down that practical interpretation, any last questions on the analysis up here? Yeah.
Can you explain one more time why, like, if it's less than the alpha value required to be accepted?
Yeah, absolutely. Let's put it down right over here. One thing I noticed when I rewrote these notes, I had a probabilistic interpretation of a p-value. It didn't make it in. So I'm glad you asked that question. Let's put it in right here. And that will hopefully address the question that you're asking there. Let me know if I lose my way and I don't quite answer it. I'm going to put it in here just as an overall statement, and we can say the p-value equals 0.0436 means, now this is not the practical interpretation, this is more probability now. There is a 4.36% chance that this study obtains a statistic p hat as extreme as 172 divided by 1386, or more extreme, we have to always say, the or more extreme means or less, what we see right up here. Let me connect that thought by changing the colors. That direction always comes from the alternative hypothesis, so it depends on the question, unfortunately. So that's why we just say or more extreme to match up with the question, or more extreme. And now let's say here, finally, this is the main component, assuming H naught that P equals 0.14 is true. So to wrap this all back to your question, this means only about 4 times out of 100, slightly more, would we get a statistic as extreme as that as more. And that means that's pretty rare. It's rarer than the 5% that we specified at the start of the problem. And so there's a small chance of obtaining this data if the null hypothesis is actually true. That means we are throwing it away and we're going to support the alternative hypothesis instead, because we are saying that's pretty rare, too rare for us to be comfortable with it and still say the proportion's 0.14. It's probably less now.
So the 0.05 is like acting as the baseline for when it can qualify, like to use H naught.
Exactly. I like how you said that. It's pretty much the baseline for having enough evidence. Exactly. Other questions or comments so far? Okay, so that's our probabilistic interpretation here. And let's add that again, just to be specific. This is not an interpretation, I would ask, but it's still valuable to know and think about because it helps us order in our minds what's really happening in a hypothesis test. So this is the probabilistic interpretation. And on this problem here, let me actually box out right through here, just to match up with the instructions in the problem. When it says test the null and alternative, these would be the major 2 things I'd be looking for here to here. Everything else is saying what we're about to do next, essentially, or extra information. So now we're ready for the so-called practical interpretation. Any other questions or comments first before we give this one a try? Okay, so the organization here is, we look at the p-value, we compare it against alpha, we find that it's less. And this comment here, rejecting the null in favor of the alternative, it's not our practical interpretation, but it tells us where to look. We're just going to interpret that statement, that we found evidence for that statement. So let's give it a try up here. We have found significant statistical evidence when we say significant statistical evidence, it's a reminder that there was a significance level, 0.05, and we found information that was significant at that level of significance, 0.05. So we have found significant statistical evidence that, now let's switch colors. So now we're just down over here. Ignore that other red dot that made it in. We're just going to read this out left to right, p less than 0.14, using the original context. We have even a key for p. These problems always are going to ask us, looks like I failed to say it exactly on this problem. On a real typical problem, it's going to ask us to say what p is. And that's our opportunity to read it out right here. The proportion of all jurors, I forgot how we wrote it out when we did it officially in our class. Again, this was a screenshot. Proportion of all jurors, I think we said that were selected for jury duty.
adopted by the court,
By the court, gotcha, that were
by the court. And live in the investigative county.
used by the court. I think it's good to emphasize that they were actual jurors used by the court and reside in the investigators county. I think that's the better description for sure. Thanks for mentioning that. It's good to have the same thing we said last day still be here on paper today. Appreciate it. So the proportion of all jurors that were used by the court and came or resided in the investigators county, that's P, we'll just say is less than 0.14. Is less than 0.14. So sometimes these problems, they honestly feel a little bit tedious because in part A, we're stating the parameter and then we have to restate it again in our overall conclusion. We don't always have to write a question that goes like that, which has all this redundancy. But the point of the redundancy is it's honestly really hard to insert what's in blue right here. We didn't say it at least once at the very start of the problem. So I just got in a habit of asking the question in that way. Sorry for all the additional writing, but the exam time length keeps into account all the writing that you do have to do as well. But we did it, folks. That's the practical conclusion in a hypothesis test. If we went the other direction, if this was like a 0.0536, it would have been greater than right here, and our statement would have gone almost identical. We would have instead said we have not found the significant statistical evidence that the alternative hypothesis is true. One thing we cannot say, it's extremely tempting. I've done it myself as a student and I've lost points on it. On homework and an exam, I got lost points on it twice. But the thing we cannot say is we found evidence that the proportion is 14%. That's one statement that hypothesis testing is really banned from, unfortunately. And the major reason is all of our methods hinged on this right here. We assumed the null hypothesis was true from the very start to measure how compatible or incompatible our data was, but that's not a way of trying to show that it's actually truth about the population. If we want to try to find out the value of P right here, we can never get it down to one number, but the best we have is a confidence interval that will give us a range of plausible values. But in hypothesis testing, we're trying to support the alternative and nothing else. Well, we did it, folks. That's our rundown of hypothesis testing in section 10.3. The only extra thing we're adding to all of this information is something called a test statistic. We don't have to have a test statistic. We ran through this test without one, but sometimes a test statistic is valuable and it will be necessary when we're doing with quantitative data, numerical data. That data turns out to be a little bit harder and the procedure takes a little bit more time. And so we're trying to make our procedures look similar so there's some parallels in the process. And that's the purpose of the next section we're about to turn to. Let me get this saved up before we go there. We probably don't need a random screenshot to serve this purpose. And here's finally our penultimate section before the big one, 10.5. So now the last section the author called an informal example of doing a hypothesis test. Now in 10.4, this is a procedure for carrying out a hypothesis test. But then 10.5 gives us the entire formula, putting every single part together. So the first thing we're taking a look at here on the notes is really kind of a throwback from section 3.5 on z-scores. So the reminder about z-scores are, what we're trying to do is count the number of standard deviations. In fact, the unit on Z is number of standard deviations that your data value is away from the mean. But that thing serves a lot of purposes. This is going to turn into a test statistic in chapter 10 and again in chapter 12. It tells you, once again, how many standard deviations you're away from a mean. But this value right here, thanks to the central limit theorem, that is a mean. So once we state a null hypothesis and put in a hypothesized value P naught, it will go here in our z-score formula. Then the data value is taking the role of P hat. That's our actual statistic we calculate from the data. For standard deviation, we just throw in the standard error, where we calculate our standard error in this new way right here. Oh, forgot to put a P hat in this location. Let me try to just sneak that in. Standard error of P hat. Let me put that in red as a quick edit that was thrown in there. Sorry about all the edits so far this semester. So once we calculate that z-test statistic, this information here is still exactly the same once we were in section 3.5. The z-test statistic will measure how many standard deviations, measured as standard errors in this problem, that your statistic p hat is away from the hypothesized value p naught. If our null hypothesis is very, very false, if it's a totally incorrect statement, we expect this to be large. There should be many standard deviations, and that's what's giving us a tiny, tiny p-value. But if the null hypothesis is reasonable, if it's not very false for our data, if our data is consistent or compatible with that statement there, then z is going to be something like 0.2, 0.5. It won't be very many standard deviations away, and our p-value is going to be suddenly really, really large. So whenever you see this information here, the z-test statistic, you're calculating that z right in here. That's the last new piece of information we need for the full hypothesis test. And so in these notes, we'll run through another example just to see how it all goes. Well, any questions or comments so far, folks, with this new information here? Okay, on these page of notes, I added the z-score formula above just so it's available. We can connect the concepts from earlier, but really this is the whole thing that's new. In fact, we didn't have to circle the standard error p hat. That was already available as well. Then, this is always good reminders in this section. Once we set these hypotheses, the next thing we always want to do is somewhere, some way, somehow, a significance level alpha must be specified. In many of the problems, they just say it for us. Test at a significance level 5% or 10% and so on. But there will be occasional problems potentially where we will decide the significance level. So we'll use typical values ranging from 0.10, if you think type 2 error is bad, to all the way down to 0.01 if type 1 error is worse. But once we calculate our z-test statistic up here, compare with the p-value and the significance level alpha, here are the only two things that can happen. Here we have a small p-value, and a small p-value means small relative to significance level alpha right here once again. Double checking that's readable with dark highlighting something dark. So with a small p-value, we reject the null hypothesis. And we'll say the study found significant evidence. Our alternative hypothesis is true. And this is the situation where no one's too happy, but science is furthered when we fail to do something. That's still good information, but this would be a large p-value. It's large only because now it's greater than or equal to alpha. Let me highlight the inequalities. That's just as important. And in this case, if we have a large p-value, recall we don't accept the null hypothesis. We simply say we fail to show the alternative is true. Essentially, in hypothesis testing, it's always about the alternative hypothesis. That's the whole thrust of the study. That's why the study even was performed in the first place. We're trying to check how reasonable our alternative is true. So those are the only two decisions we'll make. That's our reminder about that. And this is finally how we'll make them. We'll just use probabilities and our information from the normal distributions to calculate them. Any questions at the moment? Okay, so that's our p-value table. Then finally, with that new information, we should be able to go through a full problem and test some hypotheses. So let's give this a try. This problem right here came from section 10.1. All we did was state a null and alternative hypothesis. So I recopied that information down below right here. It's kind of tedious to do a same problem twice sometimes. Let's still remind ourselves of what the context was, since that was a ways away ago. it starts by telling us that the National Center for Education Statistics monitors many aspects of elementary and secondary education nationwide. And their 1996 numbers are often used as baseline to assess changes, whether they be good changes or bad changes. You could imagine they use this a lot. Every new presidential administration might have a new education secretary who has new ideas like No Child Left Behind and so on. They're using the 1996 numbers to see how successful their new policy changes might be. They told us in 1996, 34% of students had not been absent from school even once during the previous month. That was the hypothesized value that we mentioned. So note, it goes here in the null hypothesis and here in the alternative hypothesis all together. Next, it tells us in a year 2000 survey, responses from 8,302 students showed this figure had slipped to 33%. Well, that's new information, so let's write down. I mean, it's not new information, but it's not paraphrased down here, so let's write it down over here. N equals 8302 was a provided sample size. That figure of 33% is the number of successes not being absent at least once in the last 30 days for the sample. So this is a statistic. So let's call this value right here a p-hat value. P-hat is 0.33. Let's color that in green. Why not? Just to really emphasize it came from right up here. Then next it says, do these figures give significant statistical evidence of a decline in student attendance? We mentioned the moment you saw this word, there is a directionality to this test. It's not two-tailed anymore. We're doing a left-tailed test. And let me just use this color. This will be a little bit faster. So we went for less than right there. Next, the parameter P is defined. P is the proportion of all students who had not been absent even once during the previous month. I think we said last 30 days, but we can stick with this statement. Let's color code that back to blue. And that's what's appearing both right here and right here. Now, the one thing that didn't happen in this problem, well, it did happen, but they just threw it at us. They didn't give us an opportunity to select the significance level. They just told us to test the hypotheses at these values, at this level significance right here. So we want to support the alternative hypothesis. There might be a good reason they think it's declined, and they want to show that. If they can, they might be able to pivot and make some policy changes, maybe just harass the Secretary of Education until it happens. And so we're looking for a p-value that's going to be less than a 0.05. So that's the rundown of the problem so far. Any questions or comments at the moment about this question? Yeah, go ahead. Yeah.
Are we gonna I guess translate that into the n value 0.33 times n to get that p value, or is it just stay 0.33?
This one's going to stay just 0.33, which is really, really weird. So let me connect the thoughts, the question you have right here to what we did earlier on Monday's class. When we go to test the conditions right here, ordinarily we did use p-hat in this location and p-hat in this location and use them in as formulas. But these problems go way different. It's kind of wild. The very first thing we do is assume the null hypothesis is true. And that means we have something better than p-hat. We have p. So we're actually using the 0.14 that came from your null hypothesis, both right here and right here when we check the conditions. So down over here, we threw it in, oh, yes, right over here with a 0.14. And here we did put it in, but I think we just subtracted and got the value in at 1191.96 altogether. But does that make sense with that question there?
Yeah.
Gotcha.
Yes.
It is definitely kind of nasty in a way, for sure. Our standard error function right here, it really comes in two formats. If it's a hypothesis test, your value to be tested goes inside right here for your standard error. But because we have an upcoming exam, let's take a look at this, a throwback from not too long ago, but it feels like it. If you're doing a confidence interval, then with the confidence interval, let's see where we check conditions. We're using really the value of p hat, 0.0699. So if we took the 0.0699, 699, multiply against the sample size of 143, they were getting really 10 successes. This would have rounded up to 10. Our p hat was also rounded. And that's what we were checking right here. We had to use the p hat if it's a confidence interval. But if it's a hypothesis test, we're actually using that value, the 0.34, which we sometimes call p naught. Let's see if we can throw that in there just as a quick statement. P naught equals 0.34. And that was weird. Let me fix that. Microsoft Word is just getting a little bit weird. Let me put extra space here, which is equal to the value. Not sure what causes that to bounce up around. Sorry, I'm having a small fight with Microsoft Word. Equals value to be tested. Okay, I think we finally got it in. Other questions so far? Okay, thanks for asking about that question because, again, the values of p hat, the value of the 0.34, and condition checking and all the formulas get confusing when we compare the procedures. So that's absolutely the right question to ask about on these things. Now they ask us this question. How many standard deviations is the sample proportion, talking about that p hat, away from the hypothesized value? Or I call that the value to be tested. It's also the hypothesized value, the value in the null hypothesis. When you see this kind of question, the wording is honestly really kind of rude, but it's a definition check, and WebAssign is going to ask the question in this kind of way. I would probably ask, what is the test statistic? I'd be more direct about it, but that's what they're asking for us right here. We're calculating Z, the test statistic. Z is calculated in this way. The formula is right above, but we might as well just pen it in. It's going to be p hat to start. We have to subtract away from that this other value, p naught. And then we divide that whole result by this quantity, standard error, p hat. So that's our test statistic. And that means, well, it really kind of breaks down into a two-part approach. If you want to calculate this number, you can put the whole thing into your calculator, but I don't think I would even want to do that, to be honest. I think it's a good idea to break this up a little bit. Let's focus on just the denominator, find its value, then we can plug in everything else. That's more similar to how we would have done a confidence interval. So let's focus for the moment, standard error p hat. Not the same as in the chapter for confidence intervals. This one will go in by formula as p naught times 1 minus p naught and divide by the sample size n. So that's the formula we would be using for this process. That's why it was critical to find where n was, even though they gave us the value of the sample proportion of successes, 0.33. So let's plug this in and get a value. We're trying to round everything to 4 decimal places in this problem, and this is just one part of the whole problem. So I'm going to keep this one to 5 decimal places of accuracy, which is a good thought, especially for WebAssign. I'm less worried about that if it was a quiz or exam problem, however. So 0.33 goes in for, oh, that's a mistake, right? Wrong value. We're plugging in p naught, and that came right out of the null hypothesis. 0.34 is plugged in. We'll go right here. 1 minus 0.34 again, right over here. And then divide by our sample size at 8,302 students. So now we're ready for a calculator. Any questions at all, folks, to this stage? Okay, plugging it in. I'll take a slightly different approach for folks that like to go by order of operations. So if you're a fan of working inside out, here's how you could probably work this. Do 1 minus 0.34. And right away, just key in enter. It needs to multiply by 0.34. So key in times 0.34. That's our new value. Next, we divide. So hit division by 8320. Division 8320 gives us this figure in scientific notation. Oh, geez. Thanks for spotting that. O2 from up here. Thanks for seeing that. Let's see if we can get a quick edit. O2. Okay, we've got it down here. Let me just highlight that in yellow to show the change on that. And then up here, let's see. We can invert this by multiplying by 8320. Now we're back to our 0.2244. Thanks for spotting that again. Good eye. And now divide by 8302. So now we're up to that in scientific notation. For the square root, hit second power 2. We need to throw that number inside there, but not a good idea to type it in, right? That's just too much work. So up arrow, hit enter, and that should be our value right here. I have a 0.005199. Does that look right to folks so far? Awesome. I don't think I can remember those digits, so let me kind of cheat a little bit and just throw it here temporarily. So it's going to be, for standard error, we're rounding to 4 decimal places, so let's go 1, 2, 3, 4, 5. Safest thing is to round to 5 places in an intermediate computation. Number to the right is larger than 5, so this rounds up. And that would be rounding with carry, my least favorite, 0.0051. Oh, excuse me, that's going to be a 520. When that goes up by 1, this turns into a 0. That rounds up to a 2 after rounding with carry. So if we called it 4 decimal places rounded, on this problem, it actually would not have mattered. The first place is 0 anyways. But it's good to be careful. Okay, so we took a side journey. We got the standard error down. Now we return to the main question. When it's asking how many standard deviations, all they're asking for is the test statistic. And now we can bring it all together. Let's first grab our value for the numerator. It's this p hat at 0.33. We want to know how far away is the 0.33 p hat from the hypothesized value, p naught, which was the 0.34. Well, it's off by 1%, right? But that's not the kind of question we want to answer. We want to know how far away p hat is away from p naught in standard deviations. So then we divide the whole thing by our standard error of 0.00520. And throwing in that extra 0 at this point is only now serving a reminder that it's more accurate than we think when we put in that number. It's rounded to 5 decimal places. Now this is all that goes into the calculator, and we'll be in great shape on our next step. Any questions so far? Okay, so back up here, let's clear all this out. It'll be a 0.33 minus a 0.34. Don't forget to include parentheses around your whole numerator if you're putting it in one line, or if you hit enter here, then it's less of an issue. But in one line, if you divide right here, parentheses are required, and it'll be a 0.0052. Add extra 0, why not? That's now finally the value of our test statistic. This is negative 1.9231 after rounding to 4 places. And so that's telling us that our statistic p hat is almost 2 standard deviations away from the value to be tested. This might be borderline for us. We need to decide, are we rejecting the null hypothesis, H naught, or failing to do so? And now it's going to come down to the significance level alpha that's written in right here. Well, we're about ready for the p-value. The thing that's tough about a p-value computation is there are 3 formulas to doing this. The three formulas from a p-value come from the fact that in your alternative hypothesis, it could be a less than, that's one formula already. It could be a greater than, that's the second formula. Or it could be a not equals, that's the third formula. That's the reason our author has broken this down so much and why there's still one more section that ties it all together. Our tie-in section 10.5 is just saying how to calculate a p-value for any one of these three different scenarios. And they all come from your alternative hypothesis right here. We're only going to do one on these notes. We'll test the p-value for the less than and show that formula. So here's how it goes. Oh, geez, it's hard to tell how much you want to copy it. It's all good stuff. But I think we definitely want this much information at least. When we go to calculate the p-value, first thing I would probably write on paper is it's the probability that something happens. Here, we put a p-hat in when we were in the last section notes. And that's because we haven't talked about the concept of the test statistic z just yet. But once you have the z test statistic, we're in a better shape to calculate p-values. We want to calculate the probability that z is less than, and less than only because of the directionality in our alternative hypothesis, the value that we just found, negative 1.9231. So far in the process, here's what it looks like. We know that we're 1.9231 standard deviations to the left of 0.34, and we want to know what's the probability of that happening. It's honestly a pretty fast computation. We go over to a normal curve, and something wild has happened to this normal curve. It is no longer centered at 0.34. The moment you subtracted 0.34, the new center is mu is 0 now. And even better, once you divide by the standard deviation, it realigned to the standard deviation as well. The value for sigma in this normal distribution is 1. And from these notes going forward, whenever we calculate a p-value, we'll always do the test statistic z first. And that means p-values always come from here each and every time. So next thing we put in, negative 1.9231. I'll call this, it doesn't hurt to put in the number, negative 1.9231. We're shading to the left to match the directionality of the alternative hypothesis being a left tail test. And by the way, this is why we call it a left tail test. We're grabbing probability from the leftmost tail under the normal curve. So this is the moment of truth. Let's throw this into the calculator and see what we get out. We have to go to second bars, down to normal CDF. On this problem, the lower bound is definitely negative 10 power negative 9. Then we go down to option 2, and let's plug in negative 1.9231. 1.9231 goes here. We need to revise mu. It's now exactly at 0. And sigma is now exactly 1. Again, 0, 1 is just a consequence of doing the z test statistic. It standardized us to that normal distribution. Now we hit enter on this, and here's what we get out for our p-value. It's a 0.0272. 0.0272. This problem only asked us to calculate the p-value, so we're pretty much done with this one. But now we don't have time to put this on paper, but we have just a half a minute left. Let's leave this last bit to the class. According to that p-value, anyone suggest what this decision should be? Are we going to reject this null hypothesis in favor of the alternative, or are we going to fail to reject the null hypothesis? Any volunteers? Exactly. Once you make that comparison, we have rejected the null hypothesis. We need to show we have evidence. We need to say we have evidence that that's true. Exactly. Well, that's all we have time for. Sorry again for breaking a problem right in the middle, folks. That's kind of frustrating in a way, but not a problem we want to run through really fast anyways. Any questions or comments at all then before we call it a night officially? Okay, have a great night, everyone. When we come back on our Wednesday's class, I think what we'll probably do is just finish off this document. And then instead of doing 10.5, I think it'd be better if we switch gears with the rest of our time and start doing review problems. So we'll review after 10.4 and as well on Thursday. Have a great night, folks. I'll see you all on Wednesday's class.